In this video lesson, we're going to cover the concept of the spring constant. In order to do so, we're actually going to do it through the form of a figurative lab. So let's pretend that we were doing a lab in order we were testing the spring constant. On the screen, you'll see a ring stand, and you'll see a horizontal bar that goes out from the ring stand. The procedures of this lab are very simple. What we're going to do is we are going to hang a spring off of this horizontal bar that goes from the ring stand. All right, so something like that. Now, before we get started, what you would have to do is you would have to find the length of this spring unstretched. Let's make up some values. Let's say the length of the spring unstretched was 4 centimeters. All right. Now what we're going to do is we are going to start adding mass to our spring and see how much it stretches. Before we do that, let's go ahead and fill out our initial conditions. If we have 0 mass hanging from the spring, we must have 0 force that's acting on it, since force is mass times acceleration of gravity. If there's no force acting on the spring does not stretch, and therefore the stretch is 0. Okay, now let's add some mass. Let's say we added to our spring 500 grams. So I'm going to show that by erasing this. And now let's say the spring stretches once we've added the 500 grams to the spring. Okay, our mass is 500 grams, which in kilograms would be 0.5. And the force would be 0.5 times the acceleration of gravity, which is 10, or in other words, 5 newtons. So there's 5 newtons of gravitational force pulling down on the spring. When you do that, how much does it stretch? Well, the first thing we'd want to figure out is we'd want to figure out how much is the total length of the spring now. Let's make up some values. Let's say the spring now is a total of 14 centimeters. Obviously, this is not drawn to scale. If the original length was 4 centimeters, and now the length of the spring is 14 centimeters, that must mean the spring stretched or had a delta x of 10 centimeters. Notice that in the table it's in meters, so we want to make sure we record 10 centimeters as 0.1 meters. All right, let's keep going. Now let's say we take our spring and we add to it not 500 grams, but now we add 1,000 grams. So the spring would stretch even more, and now we have 1,000 grams. In terms of kilograms, that would be 1 kilogram that is added to the spring. 1 kilogram times 10 meters per second squared gives us a force of gravity of 10 newtons. And let's say we measured, and our length of our spring was now 24 centimeters. If the original length was 4 centimeters, and the total length is now 24 centimeters, the delta x, or stretch, was 20 centimeters. 20 centimeters in meters would be 0.2. Now, you can obviously get the idea. Let's just pretend that we filled in the rest of the data as we go through the experiment, and we end up getting this. So you'll see there the masses go from 0 to 2, and our forces go from 0 to 20, and our stretches go from 0 to 0.4. Now this is really good data. Most likely in a lab you wouldn't get this exact data, but to show the idea, that's the data that I chose. Now what we're going to do is we are going to graph this data. So what I'm going to do is I'm going to graph it by putting my force in newtons on the y-axis and my stretch or displacement that's measured in meters on the x-axis. There we go. Okay, so let's go ahead and do that. My stretch, which is on the x-axis, goes from 0 to 0.4. So maybe I do this. This will be 0.1, this will be 0.2, this will be 0.3, and this will be 0.4. Make sure when you graph things, you always want to go up by even intervals. Let's do the same thing for force. Force goes from 0 to a maximum of 20. So let's see, maybe what I could do is I could go up by 2s. 2, 4, 6, 8, 10 newtons, 12, 14, 16, 18, 20 newtons. All right, now let's go ahead and plot my data. My first data point is going to be 0, 0, so that'll be right here. My second data point is 0.1 in the x and 5 in the y. So 0.1 and 5 puts us right around here. The next one is 0.2 and 10. Then 0.3 and 15, which is something about right here. And then finally 0.4 and 20. All right. At that point, what I would want to do is I would want to draw a line of best fit. And the nice thing about doing computers is you have the ability to do that. If you were doing this by hand, you would probably do this with a ruler or some sort of computer program. But you'd want to draw in a line of best fit that best represents that data. Okay, so we end up having something like that. So now we have done the lab and we've graphed our data, but now we need to start analyzing some information. So what I've done on this slide is I've actually included a graph that you would most likely get from a lab. This data you can see is a little bit more real. Notice the red circles as you go up. That's your data points. And then your line of best fit is drawn in there, showing by the black line. From that, off to the side here, you'll notice that it's giving you some information about the line. Notice it's the linear fit, because it's a line of best fit. It tells you what your slope is. It tells you what your y-intercept, and then we don't really care about this stuff right there, so I'm just going to cross it out. Okay, the first thing we want to understand in physics is that the slope tells us information. So our slope of this line is 28.94 newtons per meter. I'm getting that right here. So when I take the slope of the line, that's telling me the newtons per meter. Now what is newtons per meter? What that's saying is it takes 28.94 newtons to stretch this spring 1 meter. This is known as the spring constant. The spring constant is a value that tells you how much force is required to stretch or compress a spring 1 meter. So let's go back. Let's say I was going to do this data. If I was going to do this data, I'm going to take the slope by doing y2 minus y1 over x2 minus x1. And let's say I chose this point and this point. All right, this point right here is 0.420. So the y is 20 and the x is 0.4. And then this point down at the bottom is 0, 0. So if I do 20 divided by 0.4, I end up getting that my spring constant is 50 newtons per meter. What that tells me is that it takes 50 newtons if I would want to stretch or compress this spring 1 meter. Now, just so you know, the higher the spring constant, the more stiff the spring is. For example, what if I had a spring that was 500 newtons per meter? That takes a lot more force to stretch it 1 meter than does 50. So the higher the spring constant, the stiffer the spring. So going back to this graph right here, the slope tells us our spring constant. Now, what if I wanted to make an equation for this line? Well, the equation is going to come from the form y equals mx plus b. The y value is force, and so I'm going to replace y with F. My slope is the 28.94 newtons per meter. The x is my displacement, so we're going to leave that x. And then my y-intercept is 0.179. But think about it. Our y-intercept should be 0, because if there's no stretch, there must be no force. So the fact that I have a y-intercept of 0.179 probably tells me I have some air in my lab. If I go back to this simple lab, you can see that my y-intercept is 0. So from that, we get the equation F equals 28.94 newtons per meter times x. This is the version of Hooke's law. Hooke's law states that the force applied by a spring is equal to K, which is the K constant or spring constant, times X, which is the displacement of the spring. Now the second thing that tells us a lot of information in physics is if you take the area underneath a curve. So what if I wanted to take the area underneath this curve? Okay, what is the shape? The shape is a triangle. So the area of a triangle is 1/2 base times height. Now, let's go ahead and do that. Let's actually make it simple on ourselves, and we're just going to take the area for the first 0.12. So if I stretch the spring from 0 to 0.2 meters, what is the area underneath there? Okay, let's figure that out. So our area of our triangle is 1/2. The base is 0 to 0.2, so that's 0.2 meters, times the height. The height of this, if I go up, is 6, and that's measured in newtons. Now, if I multiply 1/2 times 0.2 times 6, I end up getting 0.6 as my number. What would my units be? Well, 1/2 is unitless, meters times newtons. So I end up getting 0.6 newton times meter, which is the same thing as joules. Newton meter is the same thing as joule. So notice the area underneath the graph tells you the amount of elastic energy. Now there's another way you can calculate elastic energy if you're not given a graph. The elastic energy of any spring is calculated by taking 1/2 k, which is your spring constant, times x squared. Remember, x is the amount of stretch or compression, not the total length. All right, now that we understand that, let's use those ideas to help you with your homework. This is actually taken from worksheet 2. So the very first part of worksheet 2 has this question. Suppose in the lab, one group found that their equation of their line is force equals 1,000 Newton meters times delta x. Before I move on, make sure you can recognize that this is Hooke's law. Force equals k times delta x, or just x. So the k is 1,000 newtons per meter. That's a pretty stiff spring. Construct a graphical representation of force versus displacement, and it tells us to make our maximum displacement 0.25. So what that means is on my graph, I'm going to want to make my maximum displacement 0.25 meters. So since 0.25 is divided into 5 squares, what that means is this must be 0.05, this must be 0.1, this must be 0.15, this must be 0.2, and then 0.25 is the last one. Now how do we figure out force? Well, force is just going to be found by taking our delta x times 1,000. So if I take 0.05 times 1,000, what would my force be here when the stretch is 0.05? 0.05 times 1,000 is 50 newtons. What about 0.1? That would be 100. 0.15 would be 150. 0.2 would be 200. And then finally, 0.25 would be 250. When we do that, we figure out that we end up getting the dots right here. Or in other words, we end up getting a straight line that passes through all 5. Okay, so now that we've made our graph, number 1 wants us to graphically determine the amount of energy stored while stretching the spring described above from 0 to 10 centimeters, or in other words, from 0 to 0.1 meters. Remember, to find the energy stored in the elastic spring graphically, we just take the area under the curve. So from 0 to 10 centimeters, or 0.1, I'm going to find the area of that triangle. So 1/2 base, which is 0.1, times height, which is 100, is going to give me my energy. 1/2 times 0.1 times 100 gives me 5 as my amount of energy stored. We also could have used the equation 1/2 kx squared. 1/2, the k is 1,000, times the stretch, which is 0.1 meters, squared. If we do that calculation, we would have gotten the same answer of 5 joules. However, we did it this way first because it wanted to know it graphically, which means finding the area. So let's do the same thing in number 2. Number 2 also wants us to do this graphically to determine the amount of energy stored while stretching the spring from 15 centimeters to 25. So notice what the question's asking. It wants to know what is the amount of energy just from that 15 to 25 chunk. It does not want the total energy. So all I have to do is just simply find the area from 15 to 25, which is this right here. Now notice we get a trapezoid, but you can also break it up into a triangle and a rectangle. Okay, so let's do that. Let's take the area of the rectangle plus the area of the triangle. So the triangle is 1/2 base times height, plus the rectangle is going to be the base times the height. Now, these heights are different. The height of the triangle is different than the height of the base. Excuse me, the height of the rectangle. Okay, let's plug in our values. First of all, 1/2. The base is from here to here. So that's 0.1, because the difference between 0.15 and 0.25 is 0.1. The height 1 here is the height of the triangle. So the height of this triangle right here is going to be 250 minus 150, or 100 newtons. Plus, now let's do the rectangle. The rectangle base is still going to be the same as what it was for the triangle. So that's 0.1 times the height of the rectangle, which is going to be 150. When we add those two together, we're going to end up getting our amount stored just between 15 to 25. So 1/2 times 0.1 times 100 is going to get us 5 joules, plus, now let's do the area of the rectangle. 0.1 times 150, that's 15. And so total, there's 20 joules of energy stored additionally within that stretch. Finally, let's do the last part of the first page of your homework from worksheet 2. It says the graph at the left was made from data collected during an investigation of the relationship between the amount two different springs stretched. So essentially, they're basically doing the same thing we did in our lab, only they're doing it for two springs, the triangle spring and then the square spring. All right, so the question number 3 asks, for each spring, determine the spring constant. Do you remember how to find the spring constant from a graph? Remember, it's the slope. So let's do that. Let's do it for the square one first. When you're finding the slope of a line, it's best to take points that are very far out from each other. If I do 2 points that are close together, that's not going to give me a very good depictor or a good range of data. So what I'm going to do is I'm going to choose 2 points that are far from each other. So maybe I'll choose this point right here, and maybe I'll choose this point somewhere right there. Okay, so this point right here is going to end up being, for my x value, 2, and my y value, let's see, that's going to be somewhere around 9. And then this one right here, if I go down, it's going to be 6 for my x, and it's going to be about 29 for my y. Okay, so we're going to use my slope formula to figure that out. So y2 minus y1 over x2 minus x1. So y2 is 29, and x2 is 6. And I'm going to subtract from those y1, which is 9, and x1, which is 2. So that gets me 20 on the top and 4 on the bottom, which gives me 5, and then the units are newtons per meter. Now, I'm not going to work out number 2 because I think you'll understand how to get that. However, I will reveal the answer. You should get approximately, for the second one, the triangle one, 8 newtons per meter. Number 4 wants, for each spring, compare the amount of force required to stretch the spring 3 meters. So it wants you to find out how much force would be required to stretch the spring 3 meters and then compare them. So for the square one, force is equal to k times x, which we now know the k is 5 newtons per meter for the first one, and the stretch of 3 meters. So meters would cancel out, and it would take 15 newtons if we wanted to stretch that spring 3 meters. What about the triangle one? Well, F is equal to k times x. The k value for the triangle spring is 8 newtons per meter, and stretching that 3 meters, canceling out the meters, will give 24 newtons. So you can see it takes more force to stretch out the one that has the higher spring constant. For B, it wants us to compare the elastic energy stored at each spring 3 meters. Now, since it doesn't say it graphically, let's go ahead and use our equation. So elastic energy is just equal to 1/2 kx squared. So that's equal to 1/2, the k is 5 newtons per meter, times 3, don't forget to square it, And so 3 squared is 9 times 5 times a half. That gets me 22.5. I just calculated an energy, and so it's going to be joules. Let's do the same thing for the triangle one. So 1/2 spring constant of 8 newtons per meter times 3 squared. 3 squared is still 9 times 8 times a half gives me 36 joules. So obviously we can see the energy is greater for the triangle one as well. And then finally, question 5, determine the amount that spring 2 needs to be stretched if you wanted to store 24 joules of energy. So we're doing this one a little bit differently, but we're still using the equation for elastic energy. This time we know that we want to store 24 joules of energy. So that should be equal to 1/2. Now the K value here is going to be for the second spring, which is the triangle spring. So that's 8 newtons per meter. And we want to solve for the X. How much should we stretch it? So 24 divided by 1/2 gives us 48 equals 8 newtons per meter times X squared. 48 divided by 8 is going to give us 6. That's equal to X squared. Square root both sides. And we end up getting the amount of stretch for our spring is approximately 2.45 meters. This concludes the video on the spring constant and the worksheet number 2 that goes with it.